Okay, we'll get started with the next lecture, and we're going to shift topics to MPI. And this is probably after you get the compilers on the system, load the latest Fortran compiler, get that working. The next item that you're going to really want is GPU-aware MPI. We have instructions how to install that. It's a little bit complicated. I'm going to show you how it operates here. We'll talk tomorrow at the end of the day about looking up the instructions, how to properly install the MPI to be GPU aware to get the best performance. Okay, let's start with so message passing is what we're going to use to communicate between the different GPUs. So we can do MPI within this node of 4 GPUs, but we can also do MPI across the network to an adjacent node with another 4 GPUs. The system you are on was not really designed for optimal communications between nodes. It was really set up to work on each GPU separately, or each node separately. So you'll get good performance within the node, but between nodes, that has not been optimized. MPI, it used to be that you learn, if you were doing parallel programming, you would learn MPI, and that was all you needed to know. This would have been a much shorter presentation. It would have taken a couple hours instead of 3 days. But we have a lot more languages, a lot more technology today than just 10 years ago. So originally, when we started GPU programming, we had to send them data from CPU to CPU. So we'd have to move the data back to the CPU, pass it over to another CPU, and then write it back down to the GPU. With GPU-aware MPI, if we give it a GPU pointer, it's going to send it directly from the GPU to another GPU. This can eliminate a lot of that movement to the CPU and back. So it can make a huge difference. Plus, the GPU can drive better bandwidth. So all those together makes GPU-aware MPI really critical to get performance. There are MPICH versions that are GPU-aware, and on this system, you have access to its OpenMPI with GPU-aware. So you can also have RDMA, which is a special technology in the adapters to access that GPU memory and bypass the host. So that's RDMA, remote data. Remote data, forgotten what it actually stands for, but it's a remote data movement technology. And so you could have GPU-aware MPI, but without RDMA. So here's an example of point-to-point communication. We allocate memory on the host, initialize the device buffer, and then we send that device buffer. And then we do the opposite. We check the results and free the memory. And so we can run this to get our performance measurement of the performance from one GPU to another on the MI300A. Okay. What happens if we're on an MI300A though? We don't need 2 buffers. So what's it going to do? It's a good question. I had that question. If you do a HIP malloc, it's going to send it from the GPU. If you do a malloc, it's going to send it from the CPU, from what I understand. So it depends on how you allocate the memory. And I haven't been able to figure out how to verify that, what it's actually doing. So if we don't have GPU-aware MPI, we have to copy the data back to the host and then send it. So this can be much slower. So here's a collective communication where we're doing a reduction call. Very similar code. And then we're going to put that, you can basically tell, what's nice here is with the D underscore in front of it, we know that it's a device pointer. And if we look on an MI210, there are 8 GPUs. We have 2 chiplets and 4 sockets. So we have 8 GPUs. And this is the topology. And we see that the communication to itself is fast. XGMI within the chiplets, and then PCI between the chiplets, between the GPUs. So we get different speeds depending on who we have as our partner. And so we can set GPU 0 and 1 and communicate between those two. And how do we do that? Well, we use this environment variable, HIP visible devices, or we allocate just 2 GPUs on the node. And so HIP visible devices is going to force it to only use 0 and 1. You can make it 0 and 2, 0 and 4, and measure the different bandwidths between the different GPUs. Okay, and this is using the Ohio State University bandwidth test code. So we usually use that for our bandwidth, our official bandwidth tests. Here we're doing HIP visible devices 0 and 4. And so it's going to show a different bandwidth than we get from 0 to 1. 0 and 1 are going to be near neighbors, and 0 and 4 are going to be further apart. This is saying do a device-to-device communication. We actually set this variable when we install the MPI. We set this MCA parameter so that you don't have to supply that in each of your MPI run lines. So that's the default on the system, because I don't count on anybody remembering to do that. Any real physicist or scientist is not going to know those kind of details. So we hide it from them. Okay. And there are 2 options for GPU to GPU communication. We can actually make that communication a kernel, or we can use this SDMA engine, so a hardware engine in the device. So if we do the SDMA engine, we're not using up a SIMD unit on the GPU, but it's slower. The advantage is that we can overlap communication and computation, because we freed up that SIMD unit to do computation while the data is transferring. So blit kernel is just like a general, what the kind of kernels we've been writing. Call the kernel, and it can drive a higher bandwidth. So it's going to get higher results, but we're using up more resources. So here is the diagram for this is, I believe, the 250 at Lumi or Oak Ridge. And you can see that the GPUs have different communication links. So that's why we saw different bandwidths when we used 0 and 1. So 0 and 1 would be down here.
we should be able to get theoretically 145. And the rough rule of thumb is we're going to get 70% of that. When we did 0 and 4, see, we're only going over one link instead of these 4 here. So we're going to get us a lower amount. Now, I actually think the SDMA engine is better because it basically gets the same rate between all the GPUs. And since I'm going to be waiting on the slowest, I might as well just use the SDMA and have that SIMD unit for computation. But you can tune that depending on your application. So here we see different pairs. You can test each of them, and we see the variation in the performance. We have turned off SDMA using that environment variable. If we were on the Cray system, we have to set this variable here, MPICH GPU support enabled. On the AMD, we just need this last variable. If we enable SDMA, you see the performance is more even between the GPUs. Okay, so you can try that in your application and see what works best. Oh, and there's a new variable that we can gain the SDMA engine, so that will give us better performance, but will reduce bidirectional traffic. So this is showing on the Lumi 250X system, the difference in the performance with Blit kernels and with SDMA engines. And probably what's more important is when we're doing communication, we're often somewhere in this range where the slope is pretty steep for the message size. So if we're doing smaller messages, we're not going to get that performance. So aggregating messages into one send can make a big difference. We really need to get, 64K, 128K to start getting close to the maximum band. And you see we're at 1 meg here. That's still not that large amount of data being moved. If we're down in the smaller numbers, our bandwidth is very low. Collective communication, we're taking multiple ranks on node 0 and doing a collective. And this is across 2 nodes. So you see this is going across the network. If we are within the node, we can get a much faster, much lower latency. Not all that surprising, but it can be helpful to understand what those numbers are. On the MI300A, you have a slightly different architecture. Yeah, there's a comment in the chat that if 2 paths are being used, you can increase that bandwidth, effective bandwidth. So depending on what you're doing, that if that communication pathway is not being used, it would give you could get effectively much more bandwidth. Here's the MI300A. There's 4 of these on a node. So 1 socket for each of these, and it is uniform communication between any pair. So it's less complicated on an MI300A. And you can use this command to show the layout of the GPUs. And you see also that all of them are XGMI. So we've got all fast links for the MI300A. What is helpful is knowing what the affinity is when we start trying to do process placement to get CPUs close to the GPUs. So here we're doing a 300A system, and we're going to allocate in the first one, we're going to hip malloc. Let's look at the performance there. And so we're seeing, it needs a comma in here, but the performance here with a hip malloc is, am I reading that's about 4 times as fast as a malloc? So we're comparing that number to that number. So if we allocate on the system, we're sending the data over the from the CPUs. And this call, see if I got this right. So here we're doing DD, so we're doing device to device. In the bottom one, I don't see that, so I think we're doing CPU to CPU. There's also a library that is very popular for AI applications, and it's called RICL, or on NVIDIA, it's called NCCL, NCCL. These only do collectives. Well, it does point to point, but it's primarily used for collectives for AI workloads. Heavily optimize these calls. They're not as robust as the MPI library, but they can do some of these operations much quicker. You can mix RICL and MPI. So some of our applications have gone in and used RICL for some of the collectives to speed up their codes. And for example, PyTorch uses this for the collective communication across nodes. Across GPUs and across nodes. So it also does it within the node. Okay. So that's worth experimenting with. It is a little bit less robust, and there's still a lot of work going on to optimize it when across. It's really optimized well within a node on those 4 GPUs, but if you got multiple nodes, you may have to tune it for your network because each network is going to be different. Okay, so here's the RICL test on the MI300A. So this is, you can pull from our ROCm repository here and build and run that example. And you can try different message sizes. So we talked about MPI. You can have both MPICH and OpenMPI can support GPU-aware communication. Gray has a special MPICH version that they have on their system. OpenMPI performs quite closely to that. You can use these benchmarks from OSU. There's many of them. I've only shown you a few of them, but you can use that. One of the reasons we suggest doing this is make sure you have everything connected properly. So after you bring up the system, you may want to run some quick tests to make sure performance is what you're expecting. It is dependent on the network links between your nodes. So you have, I'm not sure what your network that you are using to connect the different GPU nodes that you have. And so it could be different than the numbers we're showing here once you go cross node. Okay. And we have a few exercises. You may want to try that out. So we have some MPI examples and you can test it out. this is really something you may want to do once the system comes up and you've built the MPI package. Any questions on the MPI? Okay. This is when you're building open MPI, you need to do this enable Rock'em flag. And that's gonna basically enable GPU aware MPI. The NHITch comes pre-built, but it's a little harder to install. And so we have not installed it. It's hard to install for Ubuntu. It's when we build a Red Hat system, the way they've packaged it will be a lot easier to install. That's it for that presentation. I think there's somewhere in here, maybe it's in the exercises where there's a note how to verify that it was built with Rock'em. Okay, so I think that's it for that presentation. I'm a little ahead of schedule. You can go ahead and try running some of those exercises, then we'll break for lunch. And we'll return at 1300, and Giacomo's going to give these presentations for the afternoon. We'll start with a realistic example of a workload for MPI with a Ghost Exchange example. Okay.